So now that we have some experience working with trees, let's talk about ways to mutate them. And there's really just two ways that you would do this: insert or delete. In this section, we're going to cover delete. You're going to get a chance to do insertion in the lab. So our goal is to implement one method: delete an item, deleting one occurrence of an item from a tree. We'll also return true to show that something was deleted, and false if it wasn't there. If the tree doesn't have the item, the tree shouldn't be changed at all. So we'll start by filling in the code template as usual. For this, we'll use the 3-branch version, which explicitly separates the case where there is a single node there. And good practice is to try to draw these out as you make things go, so you can kind of see what is happening. I'll try to visualize this along the way with some examples, but it's always worth making sure you understand what things are being modified at what time. So here is what we're working with right now. And so the base cases of when this tree is empty, when it has a single value, are pretty straightforward. If it's empty, whatever you're looking for can't be there, so you just return false. If it has a single node, which is the root, then you have two possibilities. What you're looking for is what's right there, or it's not what you're looking for. If it's not, return false. If it is, return true and set the root to be nothing, so it's deleted. In the recursive step, we're going to need to first check, is the item equal to the root? If it is, you only need to remove the root, and if not, you need to recurse in the subtrees to keep looking until you find it. So if it's the root, great, we're going to delete the root and return true. Otherwise, we have to go through all our subtrees. Now, deleting the root when there are subtrees takes a little bit of work, so we'll worry about that in a little. We can use the common strategy of using a helper method, delete root, that we haven't done yet, but we'll remember to implement that before we actually run this. This final else branch at the bottom here might look like it's done, but has a couple major problems. First off, it doesn't return anything. That's a big problem. Secondly, if one of these finds and deletes something, that doesn't stop another call from also deleting things, meaning that our original promise, which was it would delete one occurrence of an item, actually fails, right? It goes through and it deletes all the instances of the item. That's a bit of a problem. The solution to both of these is basically because our current loop doesn't actually store the value of these recursive calls. So what we should do is use the return value of the recursive calls to determine if something was deleted and whether to continue to the next subtree. So this time we're going to track to see if we actually deleted something from our recursive call. If we did, one instance of something was deleted, so we're done. We shouldn't keep looking through subtrees, we should just return true. If we didn't find something, nothing was deleted, we'll keep going. You don't need to have an else here, but just for the sake of explaining it, here it is. If you never return true in this loop, that means you never found what you were looking for, so you can return false. Now, there's one thing that we didn't quite do yet, which was implementing delete root. Note that all it really needs to do is delete the root of the tree and restructure the tree so that the root is none. There are so many ways that you could consider doing this, and we'll learn about a lot of them as you go forward in computer science. Here's a really simple one. We're just going to pick the rightmost subtree and move it to the top, so it'll become our new root, moving it up a level in the tree. So we'll delete our root by taking a random, or not random, but the rightmost subtree, popping it from the list of subtrees that we had, making that the new root, and adding to its subtrees, adding to basically the tree's subtrees, any child of that node we just promoted. This might not be super satisfying because while the result certainly is a tree, we've now changed the structure of it a fair bit, just kind of arbitrarily, in order to delete a single thing. There might be a lot of better ways to do this. Let's just take a quick look at actually running this so we can sort of see the step-by-step process. So before we had our tree structure of 1, 2, 3, 4, 5, 6, where 6 was the root, just for the sake of showing a little bit of this happening, let's add a new set of nodes here that we can make our new root, and we'll try deleting this 6. So first off, let's add T7 and T8. T7 will just be a tree of 7. So in other words, just a node with no children or anything. And T8 will have T7 as a child. And the reason I'm doing this is so that now I'll modify T6 to have T8 as a child. And so before I delete the root of 6, which is what I want to show you, let's just take a quick look at what this tree structure is going to look like. So I'm going to skip through some of these steps. Really recommend you give this a shot so you can see clearly what's happening here. But if I, zoom my way through, by the end of it, here is what I end up with. Okay, so here is my full tree. 6 is the root of everything. It has children at 4, 5, and 8. 4, as we saw before, has children 1, 2, and 3. 8 has the child 7. And so you can see here, 6 with our root has the 3 children, these 3 arrows, which respectively go to the 4, and it's 1, 2, 3, the 5, and the 7, which is a child of the 8. There's a lot of crisscross arrows here, so I really recommend consider drawing this out if you're not quite sure which things are connected where. Now, okay, we got this tree here. Let's suppose we want to delete the root, the 6, and so we'll call delete root of 6. Okay, the chosen subtree, the rightmost one that's there. Well, if we look here, which one's the rightmost one? That should be our 8. So when we select our chosen subtree by popping, we are given this 8. You can see it's been removed from the tree now, but we have a reference to it, and it's got the 8 and the 7 that we're going to make the new, or specifically the 8 that we're going to put at the top of our tree. Nextly, we're going to set, we're going to set the root to be that 8. So pretty straightforward. We go to the root, it's now going to be the 8. So if we look at our tree now, 8 is at the top. Now, we're not done yet because you can see here, great, we've removed the 6, we've put the 8 on top, but we still need to move that 7 over. So the last line of code here is to take our subtrees of the tree we're working with and include the children of the 8, in this case the 7. So last step is to do that, and now you see here we have our 8s on top, and we have 4, 5, and 7 as all of its children, and 1, 2, 3 remain the children of the 4. So great. You may want to try this with a few other values. Build your own tree, try doing the delete root so you can see exactly what happens as you go through here. Now, we're not quite done. In our implementation of delete item, suppose we delete an item that's a leaf of a tree. Like, suppose we deleted that 7, right? If we delete that, great. But the result is an empty tree, so its parent is going to have an empty tree in the subtrees list. Let's just try this over here with our with the tree that we just made, and let's see what happens if we want to delete the 7. So t6.delete item, is that the right spelling? No underscore at the front. 7. Okay, lots of steps here, so I'm going to shortcut this a little bit just to save on time. You should actually try running this. Make sure you can follow along what steps are happening along the way. And if it helps, maybe even try drawing this out on paper so you can be sure of what's happening in here. Now, as I go through here, step by step, looking for the 7, trying to delete it. We won't find the 7 till near the end because we have to go through the 4, 1, 2, 3, 5. None of those are going to be the 7 we're looking for, but we are going to find the 7 at some point, which is probably going to be near the end. Okay, so here we found our 7. We found it because it's down. Let me go back a step here. So, okay, here's our 7. Our 7 is a child of 8, our root. And so here's what's going to happen from our delete item code. We delete and we return true. So, okay, cool. We found the 7. Here it is. It's in this node that has no children or anything. We delete it. Cool. So now it's gone. And we return true. Hooray, we return true. So something's been deleted. We can end all of this and our code is good and done, right? Well, here is a trick though. Look at our tree. We got 8, it's got 2 children, which are 4 and 5. But does it really have 2 children? Let's look at its subtrees. There are 1, 2, 3 entries in the subtree list, even though we deleted that 7. And if we follow this last one, the one that was deleted, to the 7, we just have a blank node hanging out in here. It wasn't actually removed, even though it was supposed to be. So you can see that the code that we've written, sure, it deletes the value, and so when you print stuff out, it seems okay. But if we need to be looking through our subtrees and hoping that empty subtrees don't exist, well, we have this problem of now there's an empty node here that should actually have been removed completely. You might want to try the code here just to get another example of this running, and the print statements here basically show you the same thing that I just showed you. But the important note is that the tree can have empty subtrees because of the way we've implemented our code. This is probably undesired, may cause errors later on if we're counting the number of elements in a subtree list, which is a problem. So at the very least, these empty subtrees are taking up space. We don't need them there, and slowing things down. Because let's suppose we add 10 things to our subtree list and then delete them all. Now every time we want to go through the subtrees, we have to go through 10 things that are empty have been deleted. That seems like a huge waste of time. So instead, if we detect that we've deleted a leaf, we should also remove the now empty subtree. And this actually only requires a very small change. When we go over to here, if we've deleted a node and it has no children, in other words, its subtree is empty, we should remove the subtree from the list of subtrees. Now, changing a list while you're looping through it is very dangerous. You can have a lot of weird things happen. It may sometimes lose count. The only reason that we are doing this and are safe to do so is because we return immediately afterwards. And so no more loop iterations are going to happen. We don't have to worry about what happens in our next loop. It's already taken care of. So the code that we're just going to add is to remove the subtree from our list of subtrees and return true. Alternatively, if something was deleted but the subtree is not empty, we're just going to return true normally. Note that the code for deleting a now empty subtree is within a loop that iterates through the list of subtrees. So really recommend, if possible, to avoid, when you can, removing an object from a list that you are iterating through. And the only reason that this is okay right now is because we're only returning after. There's no possibility of us manipulating the list and going through another iteration. We're exiting the loop right away, and that way we can avoid this risk. Now, up to this point, you've probably wondered why we need the base case for an empty tree, since it seems like if we begin with a non-empty tree, our recursive calls should never reach an empty one. But this is only true if we assume that our subtrees doesn't contain empty trees. This may seem like a reasonable assumption, but if you don't make it explicit, there's no guarantee that this will always be true. Even though we recognize and address this by fixing up delete item just now, it's not super satisfying. What if there are other mutating methods that are here? So rather than worrying about removing empty subtrees, we're going to make this a representation invariant for our tree class. If the root is none, then subtrees needs to be an empty list. So this is an empty tree. Now, once again, I think this was mentioned before. Subtrees may be empty even if the root exists. This basically means you have one node. And the new thing we're adding here is self.subtrees should not contain any empty trees. We're going to make sure any methods that we add guarantee that we don't violate this constraint, this representation invariant. With this explicitly written down, anybody who's making changes to this tree class won't have to remember special rules about empty subtrees. Instead, they just have to remember to follow this specific guideline that we've outlined here. Now, there's a few exercises that you might want to try out just to encourage your own understanding of trees. Right now, the size 1 case in delete item is not redundant. However, it is possible to modify delete root so that you can combine this and the recursive step into one by allowing delete root to take a non-empty tree with no subtrees. So try modifying delete root and delete item so that you can simplify the code a little bit and achieve this. Another exercise is to write a new method, delete item all, that deletes every occurrence of an item from the tree. Now you have to be careful here. Think about the order in which you check the root and the subtrees, because it's possible the root has the value you're looking for, and it might be in some of the subtrees as well. You need to figure out how you can restructure things so you don't, for example, replace the root with something that should have been deleted.